Okay. Right, so now we talk about torque and angular acceleration. Right, so if we subject an object to a certain force, right, a mass of certain force from the center O, this is the tangential force and this is the radial force. The torque, right, is given by the tangential force times the radius r. Okay. Using Newton's law, F equals ma, acceleration becomes tangential acceleration. We know that tangential acceleration gives you r alpha, which is angular acceleration. Putting it all together, you got torque, you have m r squared alpha. Okay. And you realize that for a particle mass, the mr squared is actually just the moment of inertia, and you get something very pretty, which is the torque will be equals to the moment of inertia times the angular acceleration. P equals I alpha. So all this will not be in your H2, something that you will really have to look at on your own. Right, so this should not come as a surprise. The parallel is F equals ma, right? F equals ma, so you multiply by the distance, m becomes moment of inertia, a becomes angular acceleration. Translation from linear to rotational. Okay. So there are parallels, so there are easier ways to, by drawing parallels, will help you learn your stuff better. Right, so period oscillation of a physical pendulum. A physical pendulum can be a rod, a hoop, a rod with weights attached to it. The capable oscillation across an axis. The period oscillations of a physical pendulum is given by that. P equals to 2 pi square root I over n dg. Okay, so that's something for you to recall and remember. Let's look at this now. Example, a homogeneous rod oscillates in the vertical plane about the horizontal axis passing through its top. The rod is length L, 0.500 meters. Find the period oscillation of the rod. This is your typical question. Very simple but very deadly if you have not done your work. Right? Most of the time in H2, we talk about point mass, right? It's a string and then a mass at the bottom. And the period is given by square root 2 pi, because of 2 pi square root L over G, where L is the length of the string. Right? Mass does not play a factor. But here, for a rod, right, we are given the equation earlier. So we look at this. So and it's given by the moment of inertia actually matters. You realize that? Oh. So here, the moment inertia of a rod about one end is ml squared over 3, which we have repeated like I think twice just now. So we know this. We know that the d, the distance, right, is L over 2, which is the distance from the point of rotation to the center of mass. D is defined as d. Okay. So once you have that, all you have to do is submit the rest of the stuff. It's not a big issue to get this. Simple question. I have a rod and I have the same rod, but the mass is concentrated all at one end. Which one should have a larger period? Both rods are of the same mass. One rod, all the mass is concentrated at the end. The other one is this. Which one should have a larger period? What changes? So using the same idea, what happens to the I? Here the I is ml squared over 3. But if all the mass connected at one end is just ml squared, do you agree? That would just be the moment of inertia. So the moment of inertia is 3 times larger. The d becomes twice larger. This previously the d is L over 2. Now the d is just L. So on top is 3 times larger. The bottom is 2 times larger. T must become bigger. Okay? Because mass is the same. So that's the way we learn physics, where we ask ourselves simple questions like that. All right, summary page. Comparing translational and rotational quantities. Yeah, this is actually a very, very good page. As a student, I use this a lot to teach myself angular momentum and all that stuff. Okay. So basically, all the m becomes I, all the v becomes omega, all the a becomes alpha, all the f becomes t, tau. Right. The only one that I didn't really introduce is L, angular momentum. Right, but it's defined like this. It's the product of moment of inertia times the angular velocity. Alright, so collinear. Work energy power. Consider a point rotating through distance ds. The work done on it is force times ds. Okay. But because it's rotation, we should change it to radius and angle. So ds is r d theta. Right? And the f, you want to resolve to the direction of the force. So you want to resolve to perpendicular to the force. Perpendicular to the r, sorry. Right. So you have to resolve this s in the direction of the rotation. So you resolve this s by using f sine alpha, so sine phi, to in the direction of the arrow, the black arrow. This then allows you to say very quickly, right, what happens to the energy of rotation. Right, so R F sine phi is just the torque on the system. Right, so the right hand side becomes F sine phi times R becomes torque. Torque d theta is dW. Right, the work done on it is T d theta. Does the non-tangential component F do any work? Answer will be no, right? Because it's perpendicular to the distance moved. Power is just the rate of work done. So dW dt, which basically means you differentiate the theta again with time. You got tau omega. So this is so basically the whole thing here is converting what you know in kinematics, forces, dynamics, and work energy power to rotational physics, right? We have mapped the kinematics, right, the velocity, the acceleration. We have mapped the force and energy into the rotational side in the previous slide. Now we are doing it for work energy and power. Right. So this is what we have established previously, right? That tau is moment of inertia times the angular acceleration. Angular acceleration is actually just the rate of change of angular velocity. Angular velocity, if you use this mathematical method, you can speed up like that. This is also what we have established in the previous page. Then your tau becomes I dw over d theta w times d theta. So d theta cancels away. You get I omega d omega. Here, the first part, if you integrate to find w, integrate with theta over here. You can also get this chunk. Then you arrive at the interesting conclusion that the energy done on the system is the new half I omega square minus the old half I omega naught square. Okay? So it's actually quite direct and happy because you arrive at something that makes sense, because this is the rotational energy now. This is the rotational energy before, and the change in rotational energy is what the energy you give to it. So it makes sense, and we're happy. Right, ooh, here we go. Yes, fun stuff. We have no answers here. So let's see here. Which one will reach the ground first? They all have the same mass. So if you use simple work energy power conversion, they will all reach the ground with the same velocity if their masses, regardless of their masses, right? MGH loss is KE. So K is not a problem. It's translational K. But now you have rotational K involved. Oh my god. How? Okay, take your time. Think about this. Pause the video. You may want to fast forward. In the video, please fast forward. Those who are at home, fast forward the video because this pause is going to be about 5 minutes for the students at the lecture theatres to think. I better end the video. You're just watching free time.